Hello, my name is Wilson Haller. This is my Lab 4 for Physics 2. The introduction, as always, the purpose of this lab is to allow students to gain a better understanding, not only conceptually, but also computationally, of circuits. Two main principles were used in this lab, energy conservation principle and current conservation principle, and two models to show those principles were the loop rule, which says that every decrease in potential must be matched with an increase in potential for a circuit, and steady state, which shows that the current does not change in a circuit. And a preview of the main result, it was that the time that was required to discharge the circuit for RC experimentally was the same as theoretically. Both of the values agreed with each other. Here's the procedure. Everything was really the system because the surroundings were everything outside of the circuit, and outside of the circuit doesn't really have much of an effect on what goes on inside the circuit. As for my initial conditions, those are my components listed here, and on the next page the setup is shown, and the actual procedure was basically just following the lab report and answering the questions along with it. So this is the initial setup. As you can see on the left hand side, both batteries have 1.5 volts, and on the right hand side the two ammeters are placed on opposite sides of the circuit, and all the positions in red with the dots are going to be used later to calculate potential difference. We only have two resistors, that being the 47 ohm and the 100 ohm. And for the report, the ammeter prediction that we got through calculations using the loop rule was 3 volts divided by 147 ohms, because there are two resistors and you add those together. And our result was 0.02 amps, and that agreed with the experiment. When we hooked up the ammeters, it was also 0.02 amps. As for the question where we had to connect the ammeter backwards, that changes nothing because it reads current both ways. And like I said, in steady state, the current is the same. And then after you replace ammeters with voltmeters, the voltage will read 3 volts, but the ammeter reads 0 as there's no path for electrical flow because the circuit is not complete. Here are the calculations for potential differences. Voltage between A and B is 3 volts because of the EMF rule, and between all of the spaces where there's no resistors, there's no change in potential. However, in the spaces such as C and D, which are between the 47 ohm resistor, it's 0.96 volts from the calculation we used before, and between E and F, it's also 2.04 volts because there's a resistor in between points E and F. And then between points G and H, theoretically, there's going to be a change in 0 volts because ammeter technically has no resistance, but in real life this changes, as we'll see. So here's the graph of the voltage. As you can see, the voltage increases with the batteries, such as A and B. And from B to C, it's just wire, so there's no change in voltage. However, once you meet resistors, such as between C and D and between E and F, the voltage decreases because the resistors are there. The questions from this part of the lab report were the voltmeter just compares 2 points of voltage. It doesn't take any current flow away from the circuit, so that's how you're able to get readings from a non-connected circuit. The ammeter still reads 0.2 amps, and if you change the thing in the third question, the ammeter reads 0.06 amps because there's less resistance between the system because the resistors are parallel, and parallel resistors have less resistance overall. And then A, B, C, and D are the calculations for the resistance. So for the RC, when I created the RC circuit, the light dims after you run the circuit. However, the light does turn on after you connect the circuit to a capacitor, but immediately it begins to dim because drainage occurs. And that pretty much answers the third question. Amps decrease because of the capacitor, so the current starts to slow down and decrease. If you disconnect the battery, the current begins to slow and goes in the opposite direction because the capacitor inverts the direction of electrical flow. And then, the times to charge and discharge the bulb. For the 9-volt bulb, it was 3 seconds and 4.5 seconds, which is pretty fast compared to the 20 ohm bulb counterpart, which was almost double the time to charge and discharge. So this is my setup for the RC circuit. My voltmeter is on the bottom, my bulb is on the top, and my battery is on the left. So this is what the graph made from the experiment, and the 6 seconds I calculated from theory agree with this value from the graph, which is -1 over the slope, which comes out to 6 seconds. So these are the questions. If you do this in real life and use an actual ammeter, it would likely give some resistance because not everything is perfect. And in real life, all components have a non-zero resistance. So if you use a real battery, it'd be worse.